Right, welcome to OCR AS Level Physics 2019 Paper 2, Depth in Physics. I can show this on screen because OCR are a lot more cooperative than other boards that shall not be named. Question 1. Student investigates the motion of a tennis ball. We have a mass, falls vertically from rest, bounces. So we have a velocity time graph. See, it's positive to begin with. That just goes to show, folks, that you don't have to have down as negative so long as you're consistent within each situation, each question. So what are being asked first? Show that the acceleration is about 10 meters per second squared. Well, we know that acceleration is equal to rate of change of velocity. Therefore, we should find the gradient of this line. Make yourself a nice big triangle, choose a nice point. So I'm going to say that's 3.9 and then 0.4. Therefore, acceleration is equal to 3.9 divided by 0.4, and that gives me 9.75, which we know is very close to the real value, but that is close to 10. Next, show the kinetic energy of the ball before impact is that many joules. Okay, kinetic energy is equal to half mv squared. So it's equal to half times 57 grams, but that has to be in kilograms. So there's going to be 0.057 times by the speed squared. What was the speed at the top? So that is right there. So that's 4.7, methinks. And that gives me 0.629596, blah, blah, blah. We don't care. We want it to 2 sig figs. So that is 0.63 joules. Okay, the ball leaves with 80% of the kinetic energy. Calculate the magnitude of the velocity after it leaves the surface. Okay, so 0.63 times 80%, so that's 0.8. Gives us 0.504 joules. And that's again equal to half mv squared. So all we have to do is rearrange this to find v. V squared is equal to 2 lots of the energy. I'm just dropping the k there because we've only got one type here. So therefore v is the square root of all of that. And if you've spotted that there's a shortcut sort of way that we can do this, well done. I'll show you that in a second. That gives me 4.2 meters per second. But yes, there is a shorter way of doing it. We can do it in terms of proportionality. We can say that, let's just go with E here. E is proportional to V squared because mass isn't changing and half is a constant as well. Therefore, we can say that E1 divided by V1 squared is equal to E2 divided by V2 squared. Swapping these round, we find out ultimately that V2 over V1 is equal to the square root of the energies divided. And we know that this is equal to ultimately 0.8 because the second energy is only 0.8 of the original. And V1 we said was 4.7. All we have to do then is 4.7 times the square root of 0.8. And we do end up with exactly the same answer. So there we go. We don't actually need to do the long way, but I don't know, maybe they took just as long as one another. But whenever it comes to the amount of energy or a value going down or up by a factor, it's always good to get into the habit of thinking in terms of proportionality. Okay, next, complete figure 1 to show the variation velocity after it leaves the surface until it is at rest again. Okay, so people often get confused with this. Whenever something rebounds, so long as there's a very short impact time, the velocity changes direction instantaneously. So therefore, it's now no longer plus 4.7, no. It's now minus 4.2. So therefore, we need to go down to, so from here, going down all the way to minus 4.2, which is there. So there we go. Obviously, you're going to use a ruler to do a nice straight line there. That was an awful line from me. So I'm going to do that again. Oh, that's better. But then it's going to rest. So now it's carrying on going up, but it's accelerating downwards or decelerating, whichever way you want to look at it. It's still 10 or 9.8 meters per second squared. So we still need the gradient to be pretty much the same line as it was before. We could probably do this well. So basically, how long does it take to go down to a V of 0 again? Well, we can do suvat or just, acceleration is equal to change in velocity over time. Swap these two round because we're looking for a time. Time is equal to change in velocity over acceleration. Change in velocity, of course, is just that 4.2 divided by 9.8. That gives us 0.43 seconds. Okay, so 0.43, we're at here 0.48. So therefore 0.48 plus 0.43 gets us to 0.91 seconds. So we need to go all the way to 0.9, 0.91. There it is. So there's our line. Determine the maximum height reached by the ball. Height. As soon as you see something to do with height, chances are it's going to be to do with energy. Now, in this case, you can think about it in terms of energy or suvat, it doesn't matter. So you could say that EK is equal to EP, that is the GPE. So we can say that half mv squared is equal to mgh. Yeah, I tell you what, let's do it that way. So again, just like my video says about this, as soon as you see height, you know it's going to be to do with conservation of energy. Mass cancels, therefore h is equal to v squared over 2g. So we're talking about the height that it's coming off the ground at, and that was 4.2 squared divided by 2 lots of 9.8. And that gives us 0.90. It's exactly 0.9, but we are going to go to 2 sig figs, so we put that down. C. Student repeats the experiment with a different ball that is affected by air resistance. Explain how the graph now appears from the time the ball is released to the time it hits the surface. Okay, first thing we're going to say is that air resistance increases with velocity. Therefore, lines would be curved. And of course, it opposes motion. Therefore, ball would accelerate more slowly on average, and it would altogether, but on average, therefore, would take longer to reach the ground. Number 2, we have stress strain graphs. We go in until we break them. Find, compare materials J and K using the 6 terms listed below. Okay, so first things first, we know that, well, K is going to be brittle because it doesn't have a plastic region at all. Ultimate tensile strength is greater for J than K. Tell you what, I think I'm just going to write it here instead. So we can say K is brittle while J is ductile. We can say as it has a plastic region, K does not. J has a higher UTS than K. We've already used plastic, that's good. Ductile as well. We can say that K only deforms elastically because it doesn't have a bit that curves over like J. So K only deforms elastically, and then also J has a higher Young modulus, I'm just going to write E, than K, as the gradient of its linear portion, we can say elastic region is greater, we can say higher. Mark scheme says you can pick up a couple of extra marks for saying what these things mean as well. So ductile means that a material can be stretched out, can be drawn out. Brittle means it will snap without warning. Ultimate tensile strength, that's the maximum amount of stress that a material can withstand before breaking. And when things behave plastically, they will return to their original shape and size. B. We have a 3-legged wooden stool. Stool must be able to support the weight of an adult. We want a max stress of that. Estimate the minimum cross-sectional area of one leg. We're going to find the total area first. How much does a person weigh? Best to go in like 50, 100 is when you estimate something. So we're going to say that mass is around 100 kilograms. Slightly on the heavy side, but you know, we're talking about orders of magnitude here, aren't we? So we know that stress is equal to force divided by area. Force in this case is going to be mg. We're trying to find area, so we're going to swap around those two. Therefore, area is equal to mg divided by the maximum stress. So that's 100 times 9.8 divided by 2.3 times 10 to the 6 pascals. And that gives us a total area of 4.3 times 10 to the minus 4 meters squared. Therefore, divide that by 3, and we end up with 1.4 times 10 to the minus 4 meters squared. 3. Student measures diameter of a ball, 3 directions. State the name of a suitable measuring instrument. Well, of course, we want a vernier caliper, don't we, like that. Could also use a micrometer. Calculate the mean diameter of the ball, and we're going to include the absolute uncertainty as well. So let's just find the mean first, 2.52. The uncertainty is half the range. So it's going to be largest, take away smallest, divided by 2. So what's that? 0.16 divided by 2, so that's 0.08. So the volume of the ball is about that. Fine. Volume for a sphere is 4/3 pi r cubed. R, of course, being half the diameter, so that's going to be 2.52 divided by 2. So that is 1.26. Of course, that was in centimeters, so we need that in meters. So that's 0.0126. So therefore, V is equal to 4/3 pi times 0.0126 cubed. And that does give me 8.38 times 10 to the minus 6 meters cubed. Mass of the ball is that, with an uncertainty of 1 gram. Determine the density of the ball. Give your answer to an appropriate number of sig figs. Interesting. Well, we know that they've given that to 2 sig figs, so that means our answer must be to 2 sig figs too. So density is equal to mass divided by volume. So that is 23, but of course we have kilograms per meter cubed there, so we're going to say 0.023 divided by the volume, and that gives me an answer of 2,751, but we need that to 2 sig figs, so we're going to say 2,800. How very interesting. The mark scheme says 2,700, but that's if you use the value of about 8.4 times 10 to the minus 6. That is a bad move on OCR's part there. You always should use the value that you've calculated before, especially seeing that our answer should be to 3 sig figs for the volume. So, hey, I disagree with the mark scheme there. Determine the percentage uncertainty in rho. Okay, so we have, obviously we have density is equal to mass divided by volume. So what is the percentage uncertainty in each of these? Well, the percentage uncertainty in the mass is going to be that 1 divided by 23 times 100. That gives me 4.3%. Percentage uncertainty in volume, this is going to be a little bit harder. So we know that, well, volume is 4/3 pi r cubed, and the percentage uncertainty in R is going to be the same as the percentage uncertainty in D. So we're going to find it from that. So percentage uncertainty in V is equal to 3 times the percentage uncertainty in D. So that is, what was it, 0.08 divided by 2.52 times 100. So if you want to find the percentage uncertainty in a value that's calculated by timesing or dividing like we are here, you add up the percentage uncertainties. We end up with 9.5%. Therefore, the total percentage uncertainty is going to be 4.3% plus the 9.5%. So that gives me 13.8%, but we should probably do that to 2 sig figs. So we're going to say that's 14%. A lot of work for 2 marks there. B, the ball is used in an experiment with the spring. So we have L0 and then new L. Okay. So we have the student's measurements, we have L0 and L, of course. We want change in L, so that's going to be, you might call that X or even something else, doesn't really matter. So it's going to be 0.096 take away 0.078 meters, and that gives us 0.018 meters. So that's our extension. We want the force constant, so F is equal to Kx. Therefore, K is equal to F over X, our extension. So that's going to be, well, it's the weight, isn't it? So it's going to be mg divided by x. So that's our 23 grams, times that by 9.8, divide that by our extension. That gives us 12.5 newtons per meter. Seeing that our data was to 2 sig figs, we're going to say that that's 13 newtons per meter. Question C, 23 gram mass ball used to investigate upthrust. We're being asked to find the upthrust. Okay, so let's write down what we know actually what's going on with forces, shall we? We have the weight of the ball going down. We have the tension pulling upwards due to the spring, and also we have upthrust going upwards as well. And so, well, if it's in equilibrium, then we can say that obviously weight is equal to upthrust plus that tension. So that tension is equal to, according to Hooke's law again, kx. And so that was 13, wasn't it? Times by, what's the extension now? The original length of the spring was 0.078. So that means that our extension, delta L, x, whatever you want to call it, is going to be just, well, 0.01 meters. Cool. So times that by 0.01, and that gives us 0.13 newtons. We're looking for upthrust though, so, well, let's rearrange this equation here. So we have upthrust is equal to weight minus that tension, so that's going to be equal to our weight of, well, it's going to be mg, isn't it, minus the tension. So going down here, we can say that that's our, what's it, 0.023 times by 9.81, whatever. Take away our 13, take away our 0.13. So that gives us 0.0954 newtons, but we should give our answer to 2 sig figs, 0.095 newtons. Their answer is actually 0.10 newtons, but that's just because they rounded this to 0.026 newtons. So that take away the 0.13 will give you 0.10 rounded to 2 sig figs. Okay, so whenever it comes to upthrust, we know that upthrust is equal to weight of displaced liquid. So that's equal to mg. Of course, we don't have the mass of the liquid, so we can say that upthrust is equal to rho times v times g. So we're looking for density, therefore density is equal to upthrust divided by volume times g. So I'm going to use their value because I can't be bothered. So they have 0.1 divided by the volume, which is the same as the volume of the ball. What was that from way back? 8.38 times 10 to the minus 6 times 9.8. And it gives you a density of 1,218 kilograms per meter cubed. But we better give our answer 2. We'll see in that we used 2 sig figs, actually basically 1 sig figs, but we're going to put a 0 in there. So we're going to give it to 2 sig figs. So it's 1,200 kilograms per meter cubed. 4, we have a circuit with lots of resistors. So the total resistance is 50 ohms. Make your reasoning clear. Okay, well, I mean, the first thing we can do is just say that this is 30 ohms. Yes, we could prove that with our equation, but you know that if you have 2 identical resistors in parallel, the overall resistance is half that. These 3, well, it's going to be 1 over r is equal to 1 over 60 plus 1 over 60 plus 1 over 60, or in other words 3 over 60, or in other words r is equal to 60 over 3, which is 20. So when you have 3, it goes down to a third. Therefore 30 plus 20 gives you 50 ohms. Easy peasy. Calculate the PD across resistor Y. Okay, so we know that these two are going to have the same PD, but that 9 volts is being shared across that 30 ohm branch and that 20 ohm branch. They're in series with each other. So what we can say is that we take our 9 volts total, we times that by our 30 ohms, but that's relative to the total 50 ohms. So in other words, 3/5 of 9, and that gives us 5.4 volts. Calculate the charge Q passing through the resistor in 2 minutes, 120 seconds. So first thing, we need the current, don't we? Because we know ultimately we're going to do Q equals IT to find the charge, but then we need to use Ohm's law to get the current. So therefore the current is equal to V over R. You could find the current first. Maybe you should. If you want to do it one step at a time, you could also just put it all in one go into the equation there. But we do need to be careful. What voltage and what resistance are we talking about? Well, we are talking about resistor Y, so that's what we have to use. The PD across Y is 5.4 times 120 seconds, and the resistance is just that 60 ohms. I'm fairly sure that I can just say that's 5.4 times 2, and it gives me 10.8, or let's do it to 2 sig figs, so 11. And the unit, of course, is coulombs. Calculate the energy dissipated in resistor Y in 2 minutes. Well, there's like 3 different equations that we could use for this. We know that energy is equal to power times time. Power, of course, is equal to VI, so therefore energy is equal to VIT. We could also do I squared R, and then times that by the time, doesn't really matter. So that's just 5.4 times our current. I knew I should have got the current. Current is just going to be 5.4 divided by 60. It gives us 0.09 amps. There we go, we have our current. Times up by 2 minutes again, and it gives us 58.32 joules. We're just going to call that 58. B, explain how mean drift velocity. Why? OCR love mean drift velocity. How does the mean drift velocity of electrons in resistor Y compare with that in Z? Well, the equation for mean drift velocity is current is equal to N A V E. V, therefore, is equal to I over all that nonsense. N is the same, A is the same because, of course, they're the same. Resistor and, of course, the charge of electron is the same as well. Therefore, we can say that V is proportional to I. The mean drift velocity is proportional to the current. If we have a look at Z, we need to find out what the current is in Z. Voltage of Z is that 9 volts take away the 5.4 that we had for the branch on the left, so that's 3.6 volts. Therefore, current in Z is going to be V over R, so that's 3.6 divided by 60. That gives me 0.06 amps. Therefore, current in Y is, well, we said it was 0.09, didn't we, for Y. Therefore, it's 1.5 times bigger than the current in Z. That means it's the same for the drift velocity too, because they're directly proportional. Copper is a metal, carbon is a semiconductor, and ceramic is an insulator. Describe the difference between these 3 materials in terms of the number density N of free electrons, include an explanation of the term number density. N, first of all, is number of free charge carriers, could be electrons, could be something else, per unit volume. Therefore, greater N, better conduction. Copper has greatest, N out of 3, and ceramic has the least. Easy. 5, we have 2 progressive waves. Oh boy. State the amplitude of wave P. Well, we go from the midpoint, equilibrium, all the way to the top. So that looks like it's going to be 0.45 meters. So the wavelength of wave P. So we need 1 complete wave. We don't have peaks, but we do have troughs. So we're going from here to here. Thus 1.5 all the way to 5.5. Therefore, it has to be 4. Fine, let's go to 2 sig figs. Determine the phase difference in radians between P and Q. Okay, let's have a look here. I mean, what we can do is do it properly. Phase difference is equal to either difference in time divided by time period, or in this case, difference in distance divided by the wavelength. And they are the same wavelength, because otherwise we couldn't give the phase difference. So there we go. That's where the trough is for this bad boy. So therefore it's 1.5 and then 2. So the difference is just 0.5 divided by 4. And then to turn it into radians, we times by 2 pi. So actually that just means that it's pi over 4 radians. Apparently you can just write that as your answer, but let's give it as a decimal. 0.785, let's just say that's 0.79 radians. Determine the ratio of the intensities. Intensity is proportional to amplitude squared. Therefore, I1 over A1 squared is equal to I2 over A2 squared. And of course, we can just swap those round. We are talking about P and Q here though, aren't we? So let's probably do that. Therefore, intensity of P by intensity of Q is given by the ratio of the amplitudes squared. So that's equal to, what do we say it was for P? 0.45. And for Q, it looks like it's 0.15. And of course we can just do all of that squared. Oi oi, it's not just 3 squared. Ah, don't even need a calculator. Beautiful. Alright, long answer, practical question. Great. Student wishes to investigate how the friend spacing x of an interference pattern produced varies with f. Suggested that's our equation. A is the separation of the sources. D is the distance to the... Okay, so basically just Young's double slit it looks like here, folks. Right. Easy. This is just Young's double slit, but sound version. So what we can do is have 2 speakers. We have our separation there. The centers of those. We're going to have the line, which our microphone is going to be moved. Microphone can be safely conducted. My ears. Okay, so we know the Young's double slit equation, W is equal to lambda D over S. In this case, we're replacing the letters, or some of them anyway. So we have instead X is equal to lambda, still lambda D over A. And so we can say that, swapping this around, therefore lambda is equal to AX over D. And because of the wave equation V equals F lambda, that means that V over F is equal to that. So that's all that is. It's just a rejigging of Young's double slit equation. So we have our big D there, and then we have our X, how far the microphone is away from the midpoint. So what can we say? We can connect microphone to oscilloscope, move it along line parallel to A. When amplitude is a maximum, that is constructive interference. Waves are in phase. Distance from 0 to the first maximum is what they're calling X. Speakers powered by signal generator. And let's not lose sight of what the experiment was trying to find out. So we want to see how X changes with F. So we saw that V over F is equal to AX over D. Yep. What's staying the same? V is staying the same, A is staying the same, and hopefully D is staying the same as well. Therefore, X is inversely proportional to F. Change frequency of produced sound and measure X. Next, we're going to produce a graph. We always want to produce a graph. Produce graph of X against 1 over F. And we should end up with a nice straight line. And the gradient of that, of course, is going to be equal to everything else that we've crossed out here. So that's going to be, if we rearrange it, move A and D to the other side, VD over A. A couple of things we could put as well. We could measure F using time period displayed on the oscilloscope. And of course, when it comes to Young's double slit, we want the big D to be way, way larger than the slit separation. So I think that'll about do it. A couple of other things you could put as well. Have a look at the mark scheme, see what takes your fancy. 6, photoelectric effect. I like photoelectric effect. Define the term threshold frequency. So of course we're talking about this point here. That's F0. The frequency above which electrons are liberated from the surface. So use the graph to find out the threshold frequency. Well, we can see that that is 1.1. Easy. Because it has to be times 10 to the 15, doesn't it? Okay, find out the work function of silver. Right then. So people often forget this. So have a think about it. Work function is the minimum amount of energy to liberate electrons. Threshold frequency is the minimum frequency needed to do that. And so they are intrinsically linked. Phi is equal to HF. If you want to remind yourself how to do that, then just go for EK max is equal to HF minus phi. That's our just starting equation. But when we hit the threshold frequency, there is no kinetic energy left over. Therefore, HF at that point is equal to phi, and we call it HF0, don't we? So that's equal to Planck's constant times the threshold frequency that we just found. Could tidy up powers of 10, can't be bothered. And that gives us 7.29 times 10 to the minus 19 joules, but we're looking for it in electron volts. We want a smaller number because electron volts are small, we need more of them. So therefore we're going to divide by 1.6 times 10 minus 19. So actually we can just do 7.29 divided by 1.6. And that gives us 2 sig figs, 4.6 electron volts. B electrons can behave as a wave. Getting deja vu from paper 1 here. Describe the behavior of electrons which demonstrate that they have wave properties. Of course, we're talking about electron diffraction. Electrons fired at graphite lattice produce interference pattern on phosphorescent screen behind. Therefore, what does that show? That interference is occurring. Therefore, electrons must act like waves. What else could we say? What does this pattern look like? Looks like concentric rings, like so, but a little bit more concentric. And also we can say that wavelength is given by de Broglie's equation, lambda equals h over p, or mv, whichever one you want. So there we go. Is that 4 points? Yeah, I'd say that's 4 points. Mark scheme gives a couple of extra things, like just like classic diffraction stuff. We have the most diffraction when the wavelength is comparable to the size of the gap, or the size of the object that they're diffracting around. So there we go. Hope you found that helpful. If you did, please leave a like. And if you want to see any more OCR papers, then click on the card and it'll take you to the playlist. See you next time.